Hi, welcome to the fifth functions tutorial titled the exponential and logarithmic graph. In today's tutorial, we will begin by looking at the exponential graph, how it is derived, and all the equations relating to it. We will then progress on to the logarithmic graph. Just a note, the logarithmic graph is applicable only to grade 12s. The exponential graph is applicable to both 11s and 12s. In terms of what you need to know to progress on with this section, you need to have gone through the first 4 functions tutorials. It would also be advisable if you go through the section on exponents. The exponential graph indicates a relationship whereby as the independent x variable increases by a certain amount, the dependent y variable increases by an increasing amount. The standard form is y is equals to a to the power x. Let us use an example to illustrate. Think about the amount of bacteria on your smelly sports socks over a period of 4 days. On the first day, there are 2 bacteria cells. Each day, they split to form 2 new cells. Hence, on the second day, there are 4 cells. In the third day, there are 8 cells. And on the fourth day, 16. If we table this, it will read x being the amount of days, y being the amount of bacteria cells. First day 2 bacteria cells, second day 4, third day 8, and fourth day 16. If we have to sketch this on a graph, it will look like this. Notice that as x increases by the same amount all the time, y increases by an increasing amount. Its first increase was 2, its next increase was 4, its next increase was 8. If I have to continue further, its next increase will be 16, and thereafter 32, and thereafter 64, and so on. In this case, the standard equation is y is equals to 2 to the power x. I want you to use the table method to do the following examples. Press pause on your DVD player, and when you return, we'll go through it together. The first one I gave you to do read f of x is equal to 2 to the power x. Now with the exponential graph, this is an exponential graph. I'm going to try and move away from the table method, but I'm going to use it initially. We are going to be using x values. I'm going to use -2, -1, 0, 1, 2, and my corresponding y values or f of x values. When x is equal to -2, 2 to the power -2 is the same as 1 over 2 to the power +2, which is the same as 1 over 4. When x is equal to -1, that's 2 to the -1, which is 1 over 2. When x is equal to 0, that's 2 to the power 0, which is equal to 1. Remember, anything to the power 0 is always equal to 1. 2 to the power 1 is 2, 2 to the power 2 is 4. If I sketch this graph, this is my y-axis. I'm going to draw my x-axis a bit lower. X is equal to -2, let's put that over there. Y is going to equal 1/4. X is equal to -1, y is going to equal 1/2. X is equal to 0, y is going to equal 1. X is equal to 1, y is going to equal 2. X is equal to 2, y is going to equal 4. That means that my graph looks something like that. This is my graph f of x, and it passes through the point x is equal to 0, y is equal to 1. Important thing to note here is that 2 to the power x cannot ever equal 0. Notice something, it never equals 0. It doesn't matter how low x gets. 2 to the power negative 100 is still 1 over 2 to the power 100, which is some bit greater than 0. So my asymptote is that y cannot equal 0. My asymptote for this, which I'm going to draw in blue, is y cannot equal 0. So it approaches that line, but it never really reaches it. There are no x asymptotes. X can be any value, and this graph is still defined. The second one I gave you to do read g of x is equal to 3 to the power negative x. Now I'm going to do a table method for this one, but I'm only going to do a very basic table method. The first x value I'm going to plug in is negative 2, 0, and positive 2. When x is equal to negative 2, that will be 3 to the power minus 2, which is equal to 3 to the power positive 2, which is positive 9. When x is equal to 0, that's 3 to the power 0, which is 1. When x is equal to 2, that's going to be 3 to the power negative 2, which is equal to 1 over 3 squared, which is 1 over 9. Drawing the graph out, x-axis, y-axis, at an x value of negative 2, y is going to equal positive 9. At an x value of 0, y is going to equal 1. At an x value of 2, y is going to equal 1 over 9, so that's way down there. So notice something. My graph is going to do that. It's still a normal exponential graph that crosses through 0 and 1. The only difference is it's swapped around. And this is the graph g of x. Remember, my restriction or my asymptote is that y cannot equal 0, because 3 to the power negative x cannot equal 0. The next one I gave you to do read h of x is equal to 2 to the power x plus 2. I'm going to use a table method here. X and y values, or rather x and h of x values, same thing. I'm going to start my x values at negative 3, negative 2, negative 1, 0, 1, and 2. So I'm doing a bigger table method for this one just to show you what happens. When x is equal to negative 3, that's going to become 2 to the negative 3 plus 2, which is 2 to the negative 1, which is 1 over 2. If x is equal to negative 2, that's going to become negative 2 plus 2, which is 0, which means that h of x is equal to 1. When x is equal to negative 1, that's 2 to the negative 1 plus 2, which is equal to 2 to the positive 1, which is just 2. When x is equal to 0, that's 0 plus 2, which is 2. 2 to the power 2 is 4. And I'm not going to go any further than that. Let's leave it at that. Alright, now, sketching the graph. Slightly different graph to the one we've normally been sketching. Firstly, when x is equal to negative 3, y is going to equal a half. When x is equal to negative 2, y is going to equal positive 1. When x is equal to negative 1, y is going to equal 2. And when x is equal to 0, y is going to equal 4, and it's going to carry on like that. Which means that my graph will look something like that. which means that where originally it was cutting the y-axis at 1, it's now cutting the y-axis at x is equal to 0, y is equal to 4. Has anything changed? My asymptote is still the same, which says that y cannot equal 0. 2 to the power x plus 2, irrespective of the x value, that will never be 0. The only difference is the point where it should be at -2, the point where it should be cutting the y-axis, it's now over there. But that isn't an asymptote. That just means that the graph has been shifted 2 units to the left. The last one I gave you to do read j of x is equal to 4 to the power x minus 5. Now this one is interesting. Firstly, again, x can have an infinite amount of values. There are no restrictions on x. However, there are restrictions on y. 4 to the power x cannot ever equal 0. That means that 4 to the power x minus 5 cannot ever equal positive 5. That means that y cannot equal 5. Sorry, not positive 5, negative 5. Think about this. 4 to the x cannot equal 0. What I've done is I've added a negative 5. What I add to one side, I add to the other. 4 to the x minus 5 is what y is equal to, which means that y cannot ever equal negative 5. That's an asymptote, that's a restriction. If I draw it on my graph, this is my x-axis, that's my y-axis. Y cannot ever equal negative 5. So that's y is equal to negative 5. Y cannot ever equal that. That's my asymptote. Now I'm not going to do specifically a table method, but I'm just going to look at it briefly. If x is equal to, for instance, negative 2, that's going to be 4 to the power negative 2 minus 5, which is equal to 1 over 16 minus 5. 1 over 16 minus 5 is going to give me 1 over 16 minus 80 over 16, which is going to give me negative 79 over 16, which is going to be fairly close to the negative 5, but it's never going to touch it. When x is equal to negative 1, that's going to be 1 over 4 minus 5, which is the same as 1 over 4 minus 20 over 4, which is the same as negative 19 over 4, which is going to come somewhere over there. When x is equal to 0, 4 to the power 0 is 1, minus 5 is minus 4. So that means that we've now got a graph that's looking something like that. Actually, it's going to curve more steeply upward. We've got a graph that's looking like that. It's approaching the negative 5 but never really touching it. And it's going to infinity in both positive directions. This transformation has been the graph shifting down 5 units because our asymptote has moved down 5 units. In the next functions tutorial, we will be covering more on transformations. Now let us take a look at the logarithmic graph. Remember from the section under exponents and logs that a log is simply the inverse of an exponent. Hence, the logarithmic graph is simply the inverse of the exponential graph. The the logarithmic graph that we will be using has the form y is equals to log base a to the x. Let us look at how we derive that. Before we start looking at the log graph, I'm going to say, what if we have x is equal to 4 to the power y? Now think about this here. If I had y is equal to 4 to the power x, we know that this is a simple exponential graph which is going to look something like that, right? That's the equation y is equal to 4 to the power x. But now what have I done? I've swapped my x and my y values, right? So let's work on a little table method that we might have had for this one here. We would have had x values and y values. Let's start with -2, -1, 0, 1, and 2. Corresponding y values are going to be, when x is -2, that's going to be 1 over 16. X is -1, that's going to be 1 over 4. X is equal to 0, that's going to be 1. X is equal to 1, that's going to be 4. X is equal to 2, that's going to be 16. Alright. Now, what have I done? I've swapped my x and my y values around, which means that my table is now swapped around. Basically, my x values have now become my y values, and my y values have now become my x values. Is that difficult to sketch? Not really. Let's have a look at it. When my y value is -2, which I'm going to put, let's put it down here, -2, my x value is going to be 1 over 16. When my y value is -1, my x value is 1 over 4. When my y value is 0, my x value is 1. When my y value is 1, my x value is 4. And then 16 is going to be way up here. Basically, what's happening is my graph is looking like that. Bit untidy, but you get the drift. Also, for this exponential graph, we know that y cannot equal 0. That's the asymptote. For this new graph, because my x and my y values have changed, x cannot equal 0. So notice that it approaches x, but it never really touches x, and it carries on to infinity in that direction. This should be the equation x is equal to 4 to the power y. However, with graph work, we don't like equations in the form x is equal to, because x is our independent variable, y is our dependent. So we want to make y the subject of the formula. How do I do that? I use logs. To take the 4 there and bring the y down, we have to use a log, so it will be log base 4 x. Or rather, we could say y is equal to log base 4 x. Notice the relationship between these two. If I had to draw a line here, x is equal to y, wouldn't these two graphs be exactly inverse of each other, or rather mirrored of each other? If my drawing was neater, it would look very mirrored. These two are a mirror image of each other around the line x is equal to y, because they are inverse of each other. The log graph is the exact inverse of an exponential graph. Have a go at the following exercise. Press pause on your DVD player, and when you return, we'll go through it together. The first one I gave you to do read y is equal to 3 log base 2x. Now you have noticed that in the previous examples up till now I have been leaning very much towards not using the table method. In the log examples I'm not going to use the table method at all. Now the standard graph of y is equal to 2 to the power x, or rather 2 to the power x cubed, would be something like this. So that means that the log graph is going to simply come through over here, and it's going to cut the x-axis at 1. Because remember, 3 log base 2x is equal to y is equal to 0, so that's equal to 0. That means that log base 2x is equal to 0. That means that x is equal to 2 to the power 0, which means that x is equal to 1. So it cuts it at x is equal to 1, y is equal to 0, and this is the graph y is equal to 3 log 2x. Do I need to put any more information on here? Not really, not at all. That's all the information that I need to have. I did it without the table method. I did a freehand curve. In fact, I even did a freehand axis, which you don't need to do, but do the freehand curve. You don't need to do table method for everything in functions. The second one I gave you to do read negative y is equal to log base 10x. We always want y on its own, so I'm going to start by making that y is equal to negative log base 10x. Again, I'm not going to use the table method because it's long, it's drawn out, and you don't need it. Standard log graph would be over there. Except now we're looking for the negative log graph, which means that we are looking for the sort of opposite values. X values are still staying the same, but the y values are now negative. So ordinarily, where you might have an x value of positive something and a corresponding y value of positive something else, you're now going to have an x value of positive something and a y value of negative of that exact same value. So basically what's going to happen is that our new graph, instead of our old graph looked like that, our new graph is going to basically look like that. It's still going to pass through x is equal to 1, y is equal to 0, but now it's moving in the opposite direction. It's just been the standard log graph swapped around. Whoops. So remember, your standard log graph was over there. We've now just swapped it around. The third one I gave you to do read 5x is equal to 2 to the power y. We always want it in the form y is equal to. I'm going to use a log to get y down. That means log base 2 5x is equal to y, or rather y is equal to log base 2 5x. Sketching the graph. Again, not going to use table method. X-axis, y-axis, it's a standard log graph which goes like that. When y is equal to 0, x is equal to 1. Haha, not in this case. Let's look at that very carefully. If I said log base 2 5x is equal to 0, it means that 5x is equal to 2 to the power 0, which is 1, means that x is equal to 1 over 5. So our intercept is that x is equal to 1 over 5 and 0, and this is the graph log y is equal to log base 2 5x. So our intercept has changed slightly, but it's still the standard log graph shape. And that brings us to the end of the fifth functions tutorial, which dealt with the exponential and logarithmic graph. Please note that we dealt with the very basic notation of the graphs, that is of the form y is equals to a to the power x and y is equals to log base a to the x. We will expand on this notation further in the 7th tutorial titled The Basic Sketch and Transformation. In the next tutorial, we will be dealing with the trigonometric graph. It is a fun tutorial, it is a long tutorial. Before you move on to that though, I want you to go through the exercise that I left for you in the workbook.